Hello everyone. So today we are going to discuss about bulk flow and LMCD. Now, bulk flow is the movement of fluid as a whole, as the name suggests, and it is mainly uh, it takes place due to some external forces acting on it, like the difference in pressure, or rather the pressure gradient. Let's be this one as del P, pressure gradient, or if it is the gravity, or if there are some mechanical pumps. So these make up the external forces that cause a bulk flow. It is different from what we know by diffusion flow. A diffusion flow is mainly related to a molecular transport. And it is based upon the Navier-Stokes equation. Now, although the bulk flow is also related to the Navier-Stokes equation, uh, the fluid here is considered to be traveling on its as a whole. Now, in the case of a molecular transport, since the molecular uh, aspect of the fluid is considered, so collision is an important aspect of the molecular transport. Now, whenever a fluid is moving through a duct or any passage, the molecules may collide with each other. However, if there is a case where the molecules are not colliding with each other, and they are mainly colliding with the walls of the container, so that type of flow is called Newton diffusional flow. So we will come back to that in our later lectures, but today we will mainly focus on the bulk flow and LMCD flow. Now, an example of bulk flow is the blood flowing through our veins or blood through our arteries. And also in microfluidics, the bulk flow has got its significance because the fluid that flows through the microchannels can be considered to be a bulk flow, and it is mainly, as previously mentioned, due to the differences in pressure or pressure gradient. Another two more ways by which a bulk flow can occur in microfluidics is either through capillary action, or it may occur through something called an electromotive force, which is electricity driven force. So now coming to LMCD, and the word LMCD simply means this LM stands for the lubrication model. It is the lubrication model, and the CD are the two different types of flows. So the C and the C is called the equative flow, and this is basically a shear driven flow. By shear driven flow, we mean that if there are some parallel plates moving with respect to one another. So then that flow, so there is a shear force generated at the interface which causes this type of flow. The other type of flow, which is the D flow, this is mainly the drag flow. The drag flow. And this drag flow is again induced by external force like a gravity or surface tension. And now this LMC is mainly is applied in cases where there is something called thin film lubrication taking place. Thin film lubrication. Now we can define a thin film quantitatively as a film which has got a thickness h, which is a function of again distance and let's say time. The word time, the parameter time here is considered because since there is a flow involved, so the flow may change with respect to time. So one is the height, so this is the height h, and apart from being represented in being a function of this distance x, it is also a function of time because it will be traveling from one place to another with time. Now this distance for the case of films is taken less than the value L. Well, L is the lateral distance. So distance this fluid will flow after a certain time in the x direction. This is lateral distance. That means the height is very less, so that makes this as a film. Another aspect of this LMCD is the Reynolds number RE is again very less, much less than 1. So it indicates that there is a Stokes. So it implies that there is either a Stokes flow or which is also called a creeping flow. Having a negligible inertia. Now, the Navier-Stokes equation, if you write it, and again, so it is basically del u by Lt plus u dx plus u del, sorry. This will be equal to the pressure gradient plus another quantity now. Since this condition is followed here and also the height is very less, so for the case of lubrication, this equation it changes to 0 is equal to, so this part becomes, the LHS becomes absolutely equal to 0. So we have del P by del X plus so this part becomes 0 for the case of an LMCD, and we are only left with this one. So we can also if we take this in the left hand side, so it's simply del P by del X is equal to eta L square U by del Y square. This is the equation that we finally obtain. Now, if the velocity ultimately is calculated from this, so velocity as a function of y horizontal direction, or sorry, vertical direction, it is equal to 1 by eta del p by del x into y squared by 2 plus c1 y plus c2 with the two constants. Now from here we will derive the velocity for either kinetic flow, or that is for shear flow, and for drag flow. So for a shear flow we assume that we are assuming y is equal to h, so the flow at 0, which means at the base, is equal to 0, because this is equivalent to the no slip condition, and the view at a certain height, or at the top, is equal to u. So if we take it for cohesive flow, we get uy equal to 1 by 1 by eta del p by del x to y squared by 2 plus u by h y. And for the drag flow, u y is obtained as 1 by eta plus rho g sin theta into h square minus u squared by 2. Theta is the inclination angle of the surface.